Hey everyone, I hope you all are safe and doing good. So next sort is selection sort. We are done with bubble and insertion sort. Let's see what is selection sort. See, this array is given to you and you have to sort it in ascending order. I assume this. So first thing, this is also comparison based sorting. Now what I'll do in this sort, first I will select this. Also assume that the two part of the array, one is sorted, one is unsorted. But in this case, at first this is sorted part, so there is nothing in sorted array, and this complete is unsorted. So this is unsorted and this is sorted. At first there is nothing in sorted. So what we do is, from unsorted part we select the smallest element. If I want to arrange in ascending order, if you want to arrange in descending order, then you pick largest element. So in this case I just want to sort in ascending order. So in this case, from the unsorted part, we pick the smallest element. So you can check the smallest element is 1. To somehow we pick, we will discuss that process also, don't worry. So the smallest element is, we select the smallest element. And what we do? We swap this with the first element in this unsorted part. So the first element of unsorted part is 10. Smallest element from this part is 1. So we swap this with this. So after swapping, this becomes 1 is this, 8, 2, 5, 4, and 10. Now, this is my sorted portion, this is my unsorted portion. Again, we do the same process. From unsorted part, again select the smallest element is 2, and swap with the first element of the unsorted part. Or you can say now with the second element. At first, we swap with the first element, then with the second element, then third, and fourth, and fifth, like this. So the smallest is 2. We swap this with this. After swapping, this now array becomes 1. Here we have 2. 8 would be here. We have 5. We have 4. We have 10. Now this is my sorted part and this is unsorted part of the array. Repeatedly again, same process. From unsorted part, select the smallest element, that is 4. Swap it with the first element of the unsorted part. So we do the same process. 1, 2, smallest is 4. We swap this with this. 4 would be here. Here we have 5 as it is. 8 would be here and 10. Now this is my sorted part. This is my unsorted part. Like this, one by one, we keep adding in the sorted portion of the array the data. So the sorted portion keep growing. And we just keep repeating the same process until the complete array is sorted. At last, we get this much sorted part and only one element is left. So we know that no need to do any swapping. That is already at its correct position. So that's how we do. Okay. So here we select the smallest element or the largest element depending on in which order you are sorting the data. And then so basically we are selecting the position. At first, at this position, I will swap that the smallest element. Then at this position, the smallest element I'll find and I'll place that here. Right. So now the process is, now how you will find out the minimum element from this. Okay, overall idea is clear to you, but how you will find out the smallest element? We know we can search smallest element by comparing. That's not that it's a you can say big deal. So how we do this thing? Let's see. Let's now write down step by step this. At first, we have this array, sorted is this, unsorted is this. So we start from here. My I is here at first. Okay. So at first, I'll assume that my minimum is 10. Whatever at 0th index, at the starting of the unsorted, that is my minimum. So my minimum is also this. So my minimum index is also 0, or the element here is 10. So my min is also here. Okay. Now what I do is, I keep comparing this starting from this with all the elements. So for that you need another pointer or variable j. Suppose I have j. Three things we need. Okay. Now minimum is this. So I'll compare this with this. The next element, whatever at jth. Is this element less than this 10? Because this I assume that minimum element. Yes, less than 10. So it's not that we swap. No. What we do is we change my min index. My min index now becomes 1. So now my min is here. And j plus plus. Now j is here. Again check. This 2. Is this 2 now whatever the data at jth index is less than this min? Yes. So again I might change my min. Now my min becomes 2. I'm not swapping. I just do my min is now here. Now j plus plus. Again check the data. Is this less than 2? Less than whatever the min data right now? No. Okay, no need to change my min. Just do j plus plus. Is this less than 2? No. Just do j plus plus. Is this data less than whatever min data right now? Yes. Yes. In that case, again change min. Now my min becomes 5. Now my min is also here. J plus plus. But this is out of bounds, so we stop. Right. So now we get the minimum data. Because at fifth index, definitely the minimum data. So now we swap what? We swap this with this. Have to get this. We know this I pointer is still pointing to this. So we swap this with this. After swapping now, this becomes 1, 8, 2, 5, 4, and 10. So now I can say that with guarantee that this at the very first of the array I have the smallest data, the smallest element. That is for sure. Right? Okay. Now this is pass 1. This was basically pass 1. After pass 1, this is my array. Now this is my sorted portion. This is unsorted portion. Now I'll start pass 2. Now in pass 2, obviously I would be started from here. I is here. Same again. I'll consider my min is equal to also 1 because index is 1. So min is also here. Min. And now I'll start j is here. Again check same thing. Same process again repeat. I'll consider this as minimum. I keep checking the data. 2 less than 8. Yes. So I will change my min index to here. Min index now becomes 0, 1, 2, 2. So my min is here. And I'll do j plus plus. J is here. Is this 5 less than 2? No. Min would be as it is. Just j plus plus. Is this 4 less than 2? No. Just j plus plus. Is this 10 less than 2? No. Just j plus plus. And now we are out. Stop. Now min is index is 2. So this is the minimum data. At index 2, element is also 2. Now we swap this with 8. Have to get 8. We know that I is still pointing to 8. Yes. So we swap this with this. So after swapping, it becomes 1, 2, 8, 5, 4, and 10. Now this is my sorted data and this is unsorted portion. Now from unsorted portion, start from here. Now I would be this. Now I is here. Min is also here. And j is here. Again, same process. Repeat the same process. So see, if you analyze in first pass, how many comparisons you need? We check, we consider this as min element. So we compare now this with this, then this with this, then this with this with this. In worst case, with every element we compare to get the minimum element, the smallest element. So if there are n, in this case, 1, 2, 3, 4, 5, 3 and 3, 6 elements are there. How many comparison were there? This with this, 1. Then again 2, then 3, then 4, then 5. I guess 5 comparison. So n minus 1 comparison you need in worst case. Or especially in this case, only 5 comparison because only 6 elements we have. Yes. Number of swaps. How many number of swaps in first pass? There is only one swap. After finding the minimum element, the smallest element, then only we swap with the first element in the unsorted part. So only one swap. Yes. Okay. Same for pass 2. Number of comparisons. In this case, especially because the 8 we assumed minimum element, then we compare this with this. First with this, then this was the minimum, so we change this, then this with this, then this with this, then this with this. So 1, 1, 2, 3, 4, 4 comparisons. Number of swaps, 1. Yes. Same, suppose in third pass, after second pass, this is my array. So let's go for pass 3. Quickly, I'll just go for pass 3. Now after pass 2, my array is something like this. This is sorted, this is unsorted. So my I is here, my min L here, and j is here. So min is equal to 0, 1, 2, 3, 4, 5. Min is 2. I'll assume 8 is minimum. Now compare this with this. Is this element a minimum? Yes. Change the min index to here. Min index becomes 3. Now j plus plus, j is here and min is here. Again compare. Is this less than min? Yes. So j would be plus plus and min would be whatever the j is. So min is 4. Now is this less than this? No. So min would be as it is. J would be here. That is out of bound. So we stop. Right. Now whatever minimum element that is at index 4. So at index 4 we have 4. The data is this. So we swap this with the 8, the first element in this unsorted part. So after swapping, now the array is 1, 2. We swap this with this. So 4, 5 is at it, as it is, 8 is here, 10 is here. Now this is my sorted part. This is my unsorted part. Now I'll consider this as minimum element. J would be here. So I would be again, I would be plus plus now. Right? So this is my pass 3. After pass 3, this is the array. Now I'll go for pass 4. Number of comparison in pass 3. Only 4 data. Data is 4, so only 3 comparisons here we need. Only 3. Number of swap, only 1. Number of swap, only 1. After finding the minimum smallest element, we swap at the last. Only one swap. Now, next, pass 4. In pass 4, let's make this is minimum. So, min is equal to 0, 1, 2, 3, 4, 5. At third, min is 3. Check. J is here. 8 less than 5? No. So, we just do j plus plus. Min would be as it is. 10 less than 5? No. J plus plus. Min would be as it is. J plus plus, j is out. So, stop. Now, min is 3. So, at third index only we have the minimum element. So, at first, we done that I is equal to minimum. So after doing all the iteration of j, if still I and min equal, it means no need to do swapping. Or if this is not the case, then only we swap. But in worst case, suppose we need swapping. So in this case, number of swap is also 1. Number of comparison in pass 4. So if we swap 5 with 5, now array becomes something like this: 1, 2, 4, 5, 8, 10. So this is now my sorted part. This is unsorted part. Just I plus plus. So I is here. Now j is here. And I'll consider min this. So in this pass 4, number of comparison only 2. Only 2 number of comparison, only 1 swap we need in worst case. Now for this, same. Min is this. So my min is equal to I. Whatever the I is, that is 4. 0, 1, 2, 3, 4. Index 4. J is this. Is 10 less than 8? No. So min would be as it is, just j plus plus. But j is out. Stop. Min is at the fourth index only, so we swap 8 with 8. So in this case, I and min both are same, so no need to swap, right? So number of comparison, only one comparison we need in this case. So in pass, this was my pass 5. Because after pass 4, this was the array. In pass 5, I need only one comparison and one swap. Yes? After this, array becomes something like this. 1, 2, 4, 5. If we swap 8 with 8, so 8 is this and 10. So this is my sorted part, this is unsorted part. But in unsorted part, now I have only one element. So there is no need to again sort. Just this is already sorted, we stop. So how many passes we need? Pass 1, 2, 3, 4 and 5. How many elements? 6 elements. So n was 6, number of passes required are 5. So we can say number of passes required. Number of passes required in selection sort are n minus 1. N minus 1. Number of comparisons in first pass, how many comparison? 5. then 4, then 3, then 2, then 1, like this. So total comparison 1 plus 2 plus 3 plus 4. So it's like number of comparison, total number of comparison is equal to 1 plus 2 plus 3 plus up to n minus 1. Yes, same. We know what is this, the formula. N into n minus 1 divided by 2, right? After this, we take the polynomial, so it's n square. See, the formula for n natural number is, we know, that is, the formula is n into n plus 1 divided by 2. This is the formula. But here n is n minus 1. So rather than n, I'll put n minus 1. So n minus 1 into n is n minus 1 plus 1. So we can cancel 1, 1. So it becomes n. So n into n minus 1 divided by 2. If you solve this, maybe you get something like n into n by 2 minus 1 by 2. So it becomes n square by 2 minus n by 2. But we can ignore this constant and less dominating term, that is n. N square is more. So we just consider in bigger notation n square. That's why the time complexity is n square. Number of comparisons are n square. So the time complexity is also n square in worst case. That is selection sort. Okay, now see, number of swaps, I guess you get. Number of swaps in this case only one. In every pass only one swap, only 5 swap. So number of swaps are number of comparison in selection sort n square. So order of n square. Time complexity is also n square in worst case. Number of swaps required, we know 5 swaps. So basically n minus 1 swap. N minus 1. So we can say order of n. In number of swaps, it's good. It needs fewer number of swaps in selection sort. But the problem with selection sort is, if the data is already sorted, let's take, I have this data. It's already sorted. And now I want to arrange in sort in ascending order. And I want to apply selection sort. So what the sort will do? At first, this is unsorted part, this is sorted part. So I just assume this one is min element. And this is I also, this is j. So I'll just first select the minimum element from the unsorted part and swap this with the first element of the unsorted part. Min is equal to at 0th index. Index 0, 1, 2, 3, 4, 5. Now compare this with this. Is this less than 10? No. So no need to check, no need to update min, just update j. J is j plus plus. Is this less than 10? No. J plus plus. Is 30 less than 10? No. J plus plus. Is 40 less than 10? No. J plus plus. Is 50 less than 10? No. J plus plus. J is out, stop. Min is still at 0th index. So basically it's like, yeah, we have compared. How many comparison? 5. 6 elements, but how many comparisons here we have done? 5. Then with this, one comparison, then with this, 2, then 3, then 4, then 5. Number of swaps, we can check if I and min are same, no need to do swapping. So 0 swap, let's say 0 swap. But comparison are still 5. After this, the array would be 10, 15, 20, 30, 40, and 50. This is the array. And this becomes my sorted part, and this is unsorted part. Now, even after one pass, this was pass 1, we are not able to find out that this is already sorted or not. Let's take, here we have 30, here we have suppose 29. So we know that array is not already sorted, but still you need you no need any swapping. Still the minimum element is 10. So even after you compare this with this 29, is this less than 10? No. So j plus plus, and that's it. So no swapping is done. So it's not that if you haven't swapped anything, if there is no swapping, then the data is already sorted, like we have done in bubble sorting. If there is no swapping, data is already sorted. So no need to go further, but not in this case. In this case also no need, we don't need any swap. Okay. But array is not sorted. We can't say it's sorted. It's 29. It's 29. Yes. So same process you need to repeat. Even if you have sorted array, same process you need to repeat. Now you go through the past 2. Same process you need to repeat. This I'll consider minimum. This would be my j. This would be my I. Keep comparing this with, is this less than 50? No, j plus plus. Is this less than 15? No, j plus plus. Is this less than 15? No, j plus plus. Is this less than 15? No, j plus plus, and stop. So minimum is still there. No swapping we need. If I and min both are at same after all the iterations of j, no swapping is done. Still, but comparison are still 1, 2, 3, 4. 4 comparison. Swap is 0. After that, array becomes this 15, 20, 30, 40, and 50. So after pass 2, this is my sorted, this is my unsorted part. But still we don't know that it's already sorted or not. So in this case also, in the best case, even if the array is already sorted, you require 5 passes in first pass, comparison 5, then 4, then 3, then 2, then 1. Same comparison. So in this also we need number of comparison are 1, 2, 3, 4 plus up to n minus 1. So same n square. So time complexity is same n square. So even in best case means we assume that data is already sorted. So that is the best case. In that case itself, you need n square time complexity. In average case also, it's n square. So it's not at all good selection sort. In every case, time complexity is n square. You need comparison. Yeah, although swaps are less in this case rather than bubble and insertion sort, but time complexity is this. Okay. So it's definitely not adaptive. It's not adaptive because it cannot take advantage of already sorted data. Time complexity is not reducing. It's same. So it's not adaptive. Even if it's not stable as well. You can just check this. You can take here a same elements, 2 or 3 same element, and you can check after sorting, the relative ordering will be changed. You can take this example yourself and check this. So it's not stable. Yeah, it's in place. No extra memory we need. So it's in place. Space complexity is order of 1. Space complexity for selection sort is order of 1. No extra space we need. Within the same array, we do swapping kind of thing. Yes. But yeah, one point is number of swaps are less. Even if in worst case it's n. In the previous cases, in bubble insertion, it was n square. Number of swap were also n square. But here in n. So if swaps are costly, somewhere you have some requirement that swaps you should reduce number of swaps. In that case, maybe you can consider this. But otherwise, it's not good at all. Okay. Okay, so first let's try to write down what pseudocode for this or code for this. How we do? We simply, what we do is in this case, first loop is obviously for number of passes. Passes are n minus 1. Then actually the inside loop is for number of actual comparison. So 2 loops we need for sure, nested loop. So first we do what? First write down a loop. So we call selection sort. Let's name it. The method name is selection sort. And we pass the array. So let's take an array here. Now first loop, I'll take I is equal to 0 till I less than whatever size of this. Let's suppose I have int n is equal to whatever array dot length, the size. So it's n minus 1. I less than n minus 1 and I plus plus because I need only 5 passes. So from 0 till n minus 1, less than n minus 1. Yes. Next process, what we have done, we have chosen min index. So min is also whatever I is. That is my min index. Okay. Next we take j. So we just have like suppose j is equal to I plus 1. J is equal to I plus 1 because j was at first this. I consider that this is the minimum index. So I'll consider j here and start comparing. So j is equal to I plus 1. Now I'll just write down while, or you can use for loop also or while loop also. It's up to you. Okay, let's write down while or for loop. In for loop, if you want to write, so no need to initialize it again. Separately within a for loop itself, you can write for j is equal to I plus 1. and j less than n minus 1 and j plus plus. Same j is also, okay, I mean, less than 1, n minus 1. Or it should be, I guess, j should be less than equal to n minus 1. Because if n is 6, so n minus 1 is 5. Index is still 5. So j should go till 5. J is, we are starting from 1. So j is here from 1, 2, 3, 4, 5 till 5. 4 iteration. 1, 2, 3, 4, 5. 5 iteration we need for j. 1, 2, 3, 4, 5. Right? For I, we need, it should go from 0 till 5. Right? Because at last, there is only one remaining element left. So we can't, that is unnecessary if we go for this also, the next pass. Only one element we have. So no need to again go for pass 6. So pass is still here only. So 0, I would be 0, 1, 2, 3, 4 till 4. Means less than 5, less than n minus 1. But for j should go till 5, till the last. So it should be less than equal to. I guess you got why it's less than equal to, it's only less than. Now we check if array of j, if this is less than array of min, if this is the case, then we change min is equal to whatever j is. We keep doing this thing. And after this for loop now, that's it. Within this for loop, we write this thing. After this for loop, we swap, but we do not directly swap. After this, what we write, if my min is not equal to I, then only we swap. We swap I, we swap, yes, we swap I with min. Because I is still the first index, I with whatever minimum you get right now, then we swap this with this. Now we just close the outer loop as well. That is selection sort. Okay. So from loop itself, you can find out like we are running from 0 to n. Inner loop is also for, if I is 0, then inner loop is running from I plus 1 to j minus 1. I mean almost n. Then I becomes 1, then also it is running from almost n. So it's n square time. Order of n square time complexity. Number of comparison. How many times this inner loop runs, that will give you basically the time complexity. Right? So now pause the video and write down this program. Let's create a new Java class, selection sort, and in the same, I'm just taking main and I'm just copy pasting the same array, whatever we have taken in insertion sort. And we just create a method selection sort, and I'll call this and I'll pass array. Okay. Or if you want to pass array length, then also you can pass array length or array length minus 1. The size. Or size is array length only, na? So we pass only the size, that is array length, array and array length. Now, let's define this selection sort. We have int array and int n. Size, we have n. Now, outer loop will run from 0 till I less than n minus 1. And I plus plus, obviously. Now in this, we take a min. Min is equal to I. Right now, min is also I. Then we go for another loop. J is equal to I plus 1. And j less than equal to n minus 1. And j plus plus. Now we check if whatever at jth index, that data is less than whatever at min index, then I'll change my min. Min is equal to j. And after this inner loop, we check if my min is not equal to I, then we swap. I'll bypass my array, then I and min. That's it. And swap, we know how to do. I think we have done already swapping. So I'll just write down here swap. So that's how we swap. This thing we have already done many times. Now after this, let's print the array. So I'll simply call the inbuilt method arrays dot toString and I'll simply pass the array. Let's try to run this and see. Okay, index out of bound. 6 is out of bound for length 6. Okay, sorry. It's not I less than, it's j less than equal to n minus 1. Because inner loop is j. My bad. Let's run this. So it's sorted 1, 1, 4, 5, 6, 10. Now you try out yourself. I guess it's not that much tough. You can easily write down the code for this. So now you got what is selection sort, right? Now, okay, it's not at all good because in every case the time complexity is n square for selection sort. Yeah, number of swaps are less than the other sorts, bubble and insertion, but time complexity is not at all good. So for large data, it's not good. Maybe for smaller data, you can go for this. Now in the next lecture, we'll see what is quick sort. So all the basic sorting is done, bubble, insertion, selection. Now we'll go for efficient sorting algorithm, quick, merge, and these. So that's it for this lecture. Now I'll see you in the next lecture. Bye bye. Take care.